Hi everyone, this is Tarun. I work as engineering lead at SquadVoice. This is my debut as a conference speaker. I am excited as well as nervous. My legs were literally shaking 15 minutes before. So if you have any feedback, any questions, feel free to shoot me DM over Twitter. My Twitter handle is down there. So coming to talk, the talk is about looking beyond B-tree indexes for performance optimization. It is not an opposite view, it is an alternative view. It is about looking beyond B-tree indexes. So while we think of performance optimization, we think of let's create an index. And what is an index in Postgres by default? It is a B-tree index. So what are the alternatives for creating B-tree index? Where does the B-tree indexes fail? What are the options that you can explore? And how does this process has evolved over the different Postgres versions, 9.4, 9.6, 10, 11, 12, etc. So first, let's look at the problem statement that we are trying to solve here. So consider we have a table. The table has few columns like name, date of birth, state of birth, and what is the sex. So it can be thought of as like a population table, population register table, where entries are being added daily. Some assumptions about those tables are the entries in this table are growing like a million in a day. Like population of India is growing million in a day, those entries in this table are also growing like millions in a day. Now we need to find out who are the people born in certain states over a period of time. So in order to find that out, what do you usually do? You write a SQL query which goes something like select star from population, where state of birth in these states and date of birth between these time ranges. So what happens after that is that this query takes eternity to load. Now why it is taking eternity to load? So XP Analyze to rescue here. So for uninitiated, what is XP Analyze is? XP Analyze is a tool provided by Postgres that shows you how the query is actually performing on your DB engine. It consists of two parts. First is explain, second is analyze. Explain shows what the planner planned to do, while analyze actually executes the query and shows what the planner actually did. So those are two different bits, explain and analyze. People usually talk them in conjecture, but those are two different bits. So this is one dummy explain analyze, which just shows that it is doing a sequence scan over population table, what is the cost attached to it, what is the actual cost, what is the planned cost, etc., etc. So these are the different stats that are thrown to us by explain analyze. So we ran explain analyze, and in our case, the query planner was doing a sequence scan over a million record. So you can assume that if it is doing a sequence scan over a million records, it's bound to be slow. And if it's bound to be slow, it will take that loading cursor you see, it will be like, your life will be like that only. So how to avoid a sequence scan? So that is the question that we also had, that how do we avoid the sequence scan? Indexing for the win. So we said, okay, let's implement indexing. Currently it's doing sequence scan. Maybe we'll implement indexing. The sequence scan will be gone. So we also ran a command, create index, index name on population, on certain columns on which it was being accessed. We created an index. Actually, we created concurrently. Just for this talk, it is create index. Result. After we created the index, the query planner was still doing sequence scan. I mean, we created the index, we created what was needed, we created a B-tree index, but why is the planner still doing sequence scan? So how does a planner choose whether to use a sequence scan or an index scan? So in planner's term, everything is related to a cost. And that cost is looks something like this, which is cost of a sequence operation into number of tuples it needs to read sequentially, summation cost of a random operation into number of tuples it needs to read randomly, etc., etc. So the cost of sequence operation is denoted by sequence page cost in Postgres, and cost of a random operation is denoted by random page cost. The default value of, it turned out the default value of random page cost is 4, while the default value of sequence page cost is 1 in Postgres. What does that mean is, that means a graph like that, which shows that over a time, when your query selectivity increases, by query selectivity, the number of rows it is being returned by the query increases, the cost of index scan increases exponentially, while the cost of sequence scan remains constant. Why? Because sequence scan has to sequentially scan the whole table. It doesn't matter how many rows are they being returned. So that is why when the number of rows are being returned high, Postgres chooses to sequence scan versus it should do versus index scan. Due to these values, Postgres chooses to do sequence scan. We can change these values per table and index-based usage statistics. Some people suggest that maybe you can make sequence page cost equal to random page cost or lower the value of random page cost. You can do that, but there are two conditions for it. First is if your DB or table can fit into RAM or the cache of your database server, then you must do it. The second is if you're using an SSD, then you must do it because the cost of random scan in case of SSD is much lower than while you do magnetic storage or SDDs. So that is the reason our planner was doing a sequence scan. So we went again back to the research mode. What can we do next? We came across this term called as block range index. It is being marketed as an index for big data or big tables. So we just looked at what is the block range index is about, what is this fuzz is about. So to illustrate what is block range index is, first let's look at what is B-tree index is about. So in B-tree index, your leaf node contains a pointer to the actual table row. So suppose you have a B-tree index like this, 1 is pointed to a table in the database, 2 is pointing to a table in your 2 is pointing to a row in the table, 5 is pointing to a row in the table, etc., etc. That's how B-tree indexes are structured. While what happens in block range indexes, how block range index operates is they create a block, and what that blocks contains is that blocks contains the summary information. So for example, in case of B-tree index, you saw that you have a pointer pointing to 1, 2, 5, 6, while in case of Brin index or block range index, what you have is minimum value and a maximum value. So it says that this block has a minimum value of 1 and a maximum value of 6. The next block has a minimum value of 9, maximum value of 12, and the minimum value of 1 to 6 is contained in pages 1 and 2. The maximum value between 9 to 12 is contained in pages 3. So what that actually means is, suppose you are searching for a table which points to row number 5, right? So it will just see, okay, row number 5 is lies between 1 and 6, so it may lie in page 1 and 2, so it will bring that page 1 and 2 in into your disk and then compare the results. So what are some properties of Brin index? So search over Brin index is like an index search plus sequential search. What does that mean is, suppose you have a Brin index like that in the middle. That Brin index is indexed over a date column which has different blocks. That this block contains data between 1st Jan to 5th Jan. Other block contain data between 6th Jan to 8th Jan and so forth. And you execute a SQL query which says that provide me data between 6th Jan to 13th Jan. So what will Brin index will do is it will prune what are the unnecessary blocks. In this case, 1st block and 4th block are unnecessary blocks because those do not lie in my date range 6 to 13 Jan. It will just say, okay, 2nd and 3rd block lie in that date range, and what are the pages that are there in my 2nd page and 2nd block and 3rd block. Pages are 4, 5, 6, 7, 8, 9. So it will bring only those pages into memory and search over those pages. Right? While in B-tree index, you have a layer in which each entry is being indexed, right? So it will have to search each entry to see whether it matches 5, whether it matches 5, whether it matches 5. But in this case, it can just prune the unnecessary tables by just looking at the summary information that is stored in my Brin index. So there's a peculiar property about Brin indexes. They are preferred only when there is a strong correlation between the data being stored in the disk and the column values. Example for that can be sequence numbers, timestamps, order dates, etc., etc. Basically, the funda is that the column that is being indexed should have a physical correlation in how it is being stored in the disk. And why they are preferred that way? So again, consider an example. If you do not have that property in your database and you index a column which is randomly there in the disk and does not have any specified order, what that would do is your blocks will have every page because it is being randomly done. And when you say provide me the data between 6 Jan to 13 Jan, it will essentially fetch all the pages that are there in your DB, and basically what that would end up doing is making it worse than my sequence scan. So that is why Brin index is preferred when there is a strong correlation between data being stored in the disk and the column values being stored. And due to the way they are stored, because basically B-tree stores each leaf node and a pointer to the row in the DB, but Brin does not store all of that information. Brin stores just the information which page and which range does the value contain in. Due to the way they are stored, they occupy way lesser space than usual indexes, and maintenance overhead is way less. By way less, I mean less than 100x. If your B-tree index is 1 GB, your Brin would be in size of KBs. That is the size difference that you see while using Brin index. And that is why it is being marketed as a big data index, because when your data grows big, your B-tree indexes become even bigger. The maintenance overhead kicks in. That is why Brin index comes in. That is where Brin index comes in, because it occupies way less space. The maintenance overhead is way less. So that is why it is being marketed as a big data index. So with all of this information, we wanted to give Brin index a try. We said, okay, let's create a Brin index over the column, and the only difference that you would see here is the using Brin syntax that is there. We implemented Brin index. What was the result? The result was no success. The planner was still doing sequence scan. Why it was still doing the sequence scan? Because again, the basics of planner does not change. It still has a random page cost of 4. It still has sequence page cost of 1. But we had a takeaway here that Brin succeeds only when search target is a narrow set of values. It is being marketed as a big data index because the size is way lesser of the index, the maintenance overhead is way less, but it's like B-tree index, it also succeeds when search target is a narrow set of values. So that's, Brin index has also gone here. But Brin index seeded an idea that if you think about it, Brin index is like a virtual partitioning where partitions are being sequentially scanned. So as I said, that Brin index contains different blocks. All of those blocks can be thought of as a partition. And once we know that, okay, my value contains in this partition, we sequentially scan those partitions. So Brin index is like a virtual partitioning that you have in your database. So that led us to thought that, okay, now we are getting somewhere. Maybe we are close to solution. But while we were exploring Brin index, we also came across materialized views. The primary reason was I read somewhere that materialized views optimizes your performance, so I wanted to give it a try. And the image is taken from Martin Klapman blog. He has a fantastic book, Building Data Intensive Applications. Aspiring DBAs and application developers must read that book in order to understand what happens in the DB. So we also gave it materialized view a try. What is materialized views are? Materialized views are like normal DB views, but they are just materialized into your database. By materialized, what do I mean? I'll explain. Similar to database views, but the results are persisted in the table versus querying being routed to main table always. They are always persisted in the table. They create a table out of your main table, while the normal views, they are just a view layer over top of it. When you query the normal view, the query still routes to main table, while in case of materialized view, it is not the case. Since they are like tables, they can be indexed, they can be vacuumed, they can be partitioned, etc., etc. And we figured out that materialized views are not performance optimization techniques. They are ideal for capturing frequently used joins, aggregation. So suppose you have a query that you run very frequently that joins across 5 tables, and your operations or some people usually write that query and run that query. Maybe you can provide a materialized view over that query for them. And they can just use that view instead of joining over 5 tables, knowing about the complex application logic that you have built, etc., etc. But there comes a downside that in order to update materialized views with the new data in the original table, you'll need to manually refresh the view. So they are not real time. You can use schedule job, etc., to refresh materialized views, and you can refresh those materialized views concurrently also. So with Brin indexing, this also seeded an idea that maybe if we have smaller tables with indexes, that would do it. Why was not index scan previously working? Because the table was large, index was returning a lot of values, while the random page cost and sequence page cost was not making sense for a planner to do index scan. So maybe if we can have smaller values with indexes, that would do the job. What is the smaller value with indexes looks like in Postgres? Partitioning. What is partitioning is, the main idea is that you have a massive table, which you call a parent table. You split that table into multiple smaller tables that you call partition or child tables. And this enables your quick query execution by pruning what are the unnecessary partitions out. So you have smaller tables, smaller indexes. Those tables can be bought into memory. Those indexes can be directly bought into disk. What does that look like in real life? This is what it looks like. Suppose you have a population table, you partition it by date, that population table, child table for January month, child table for February month, child table for March month. So you partitioned a big population table into multiple small tables. So that is what partitioning looks like. So before Postgres 10, there was only one way of doing partitioning, which is inheritance partitioning. The people who are familiar with object-oriented programming concepts might relate what is inheritance is. That is the exact way inheritance-based partitioning is being implemented in Postgres. Concept is you have a parent table, you inherit a child table out of that parent table. You add non-overlapping checks over those child tables. So those checks can be something like add a check that my date of birth has to be in January, add a check that my date of birth has to be in February, add a check that my date of birth has to be in March. So you created a multiple child partitions that are inherited from my parent population table. You add indexes to the key columns, and you add triggers to insert data into desired partition. So if you insert in the main population table, you have to add triggers and rules in order to route that insert into appropriate child table. I'll explain again with the diagram how does that look like. So in inheritance-based partitioning, one of the downsides is that we have to use rules and triggers in order to route an insert or an update to parent table or to an appropriate child table. What does that look like? That looks like something like this. Suppose you have an insert coming in on my population table. You have to create a trigger that says before inserting on my population table, do this trigger. In that trigger, you will write some code which says like if the insertion is coming for January month, route it to my January table. If the insertion is coming for February month, route it to February table. If the insertion is coming for March month, route it to that table. What that would also mean is suppose in future you have some data for April, right? So you need to make sure that you update your trigger, you need to make sure you create your child tables, etc., etc., right? So that is a manual maintenance overhead that comes with making those triggers and making those inheritance-based partitioning triggers. Again, the second disadvantage of inheritance-based partitioning is when querying the parent table, the query references all the rows of the parent table as well as the child. What does that mean? That means if there is a query that is coming in which says that provide me data for month January, that is coming on my parent table, what it would do is it would go to January table partition also, it would go to February partition also, it would go to March partition also, say do you have the data for January, do you have the data for January, do you have the data for January. After combining all this result, it sends back to my user again, and it also queries the parent table which was the main table using which it was partitioned. So that is kind of bummer and it can lead to duplicate data being returned from our query, etc., right? Thankfully, there is a way to override this, which is constraint exclusion. Constraint exclusion parameters needs to be enabled for query optimization to work. What does that look like is if you have constraint exclusion parameter as set, what it would now do is it will still go to the parent table, but now it will just go to, since you have said that provide me data for January, it will say okay, I have checked for January in my January table, I'll go to just the January table, I'll exclude February, I'll exclude March, and I'll combine the data from parent table and the January table and send it back to my user, right? So the constraint exclusion provides that pruning, but it is still inefficient because it still queries the parent table also, right? So you have to make sure that my parent table is always empty, which is again a manual overhead, a thing that you need to add a check for or something you need to do about it. Yeah, database level. Yeah. So inheritance-based partition, what are some of other properties of inheritance-based partitioning is child tables can have more columns and indexes than parent table. So it's like normal in inheritance, right? You can override the things that you specified in your parent. Inheritance-based partitioning was the only way before Postgres 10. Indexes and constraints that you create on your parent table does not get automatically created on child. So indexes and constraints that you have in your parent table, you have to manually create on all of the childs. Due to all of these things, we decided not to use inheritance-based partitioning. Inheritance-based partitioning was not majorly used before Postgres 10 came out. Postgres 10 introduced something called as declarative partitioning, or some people might call it native partitioning, which is a partitioning in true sense, basically. What do you do in declarative partitioning is you create a parent partition table. One caveat here is you cannot turn a regular table into a partition table. You create child partition table from that parent partition table that you just created above. So that is all you need to do to enable declarative partitioning. So as you see in the first command, you see partition by method, right? So Postgres 10 or 11 provides different means to do partitioning. First mean is list-based partitioning. What does list-based partitioning is that you can partition basis the value of a list. That list can be something like state of birth, it can be payment status. You can say that, okay, I want to partition by payment status. My delivered orders goes into one partition, my failed orders go to another partition, my rescheduled orders goes to another partition. So this is the use case for list-based partitioning. The other is range-based partitioning, where you can partition by range of values. Those can be like date of birth, day, month, year. You can say, for example, I said that you partition by January data in one table, February data in one table, March data in one table. So that is the range-based partitioning that Postgres provides. Third and the most interesting is hash-based partitioning. Hash-based partitioning is introduced in Postgres 11. It is useful for the case where you do not have distinct values on which you can partition. So you just want to say that, okay, I have big table, I want to partition this into 4 tables, right? So that is where hash-based partitioning comes in. Where you can specify modulo-based partitioning. As I said, you want to specify 4 partition, you specify modulo of 4. If you want to partition into 6 tables, you specify modulo of 6. So what are the upsides? What are the new things that declarative partitioning provided that my inheritance-based partitioning was not able to provide? First thing is that new inserts are automatically routed to partition table basis the partition key. So in inheritance-based partitioning, you have to add triggers, but here new inserts or updates are being automatically routed to my appropriate child table. So if I say that insert into my parent table the data for January, it will automatically get routed to my January table. You don't have to add triggers, anything like that for declarative-based partitioning to work. Updates are also automatically routed to partition table, basically partition key. This is added in Postgres 11. What that would mean is, suppose you have a partition for April month. In that partition, you want to update a value of partition key that, okay, this row does not belong to April month. This row actually belongs to my January month. You update the value there, and it will automatically get routed to my January table. This was not possible in Postgres 10. This came in Postgres 11. And it is not update, it is delete plus insert. It will delete from my April table, it will insert then again in my January table. So that is one of the major updates that Postgres did in Postgres 11. Another is, there is a provision to call it something called as default partition. So why is that default partition helpful is because application codes are ever changing. So default partitioning helps in a scenario where suppose you have made partitions for over the year like January, February, March up to December, and you enter a new year, right? Now you have to manually remember, okay, since I enter my new year, I need to create new partitions, right? If you don't create new partitions, what will happen if there is an insert on the primary table, inserts will fail, your application will go down, right? How that changes with Postgres 11 is you have something called as default partition. You can specify that this partition is default. If this value does not belong to any of the partitions, send it to my default partition, right? And how that would help in our queries is basically it will query the default partition and it will query the relevant partition also. So that is one of the, again, updates provided in PG11, one of the major updates with regards to declarative partitioning. I can hear you.
When the data goes into a default partition, and when you run select,
Right.
Would that do a table scan or because it doesn't have a partition key defined?
Right. So good question. So what it will do is it will do a table scan on your default partition, and whenever you do any kind of query you will do, it will go to default partition for sure in order to search whether there is some data contained in default partition for that thing. And in default partition also it is just a normal table, so you can create indexes, everything like that in default partitions. I hope that answers.
Let's say if I specify a where clause, obviously we have a partition.
Right. That case also it goes to default partition because it does not know what does your default partition contains. It might happen that after some data has been inserted into default partition, you created a child partition, right? And you forgot rerouting the default partition data to my child partition, so that default partition data still contains. Manually, it has to be done manually. Right, yep. Another property of declarative-based partitioning is improved query support. In case of inheritance-based partitioning, you saw that it queries the main table as well as the child table, while in case of declarative-based partitioning, it sees that, okay, I need data for January month. It does not query the parent table. Because it knows that parent is my partition table, it directly goes to my January table and say, okay, give me the data for January month and send it back to my to the user. And it is being done on runtime versus compile time. What that would mean is, in constraint exclusion, you cannot have dynamic parameters, while in case of declarative-based partitioning, you can have dynamic values. For example, in where clause, you specify first character of this sentence A, right? Now, that kind of query cannot be done if you are doing constraint-based exclusion, but in case of declarative partitioning, since pruning is done on runtime, that kind of thing is supported. So in declarative-based partitioning, index created on parent table automatically gets routed to child table. Not only the index, the unique values also. So if there is a create index command on parent table, it will just say copy, 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 copy over all of the my child tables, right? So that is again added in Postgres 11. In declarative-based partitioning, you are allowed to have a primary key and unique keys, but those keys have to be part of your partition key also, right? What that would mean is that if you are partitioning by your ID column, you cannot have a unique index on name column. You have to have a unique index on ID column itself. If you want to a unique index on name column, partition by name column. This create unique index command would fail in case you have an index on ID column as the specified in diagram. And diagram also specifies how do you do hash-based partitioning. You just say, I have a big table, I want to divide that big table into 3 tables. You say modulus 3, remainder 0, do this table, modulo 3, remainder 1, do this table, modulus 3, remainder 2, insert to that table. So that is how you do hash-based partitioning also. Some of the things about declarative-based partitioning is partitions are not allowed to have their own columns, as the case with inheritance partitioning was. Support for foreign keys is very limited in declarative-based partitioning. What that means is you can have any outgoing foreign key, but you cannot have any incoming foreign key to my partition table. What that would mean is you can add a foreign key to my population table, but you cannot reference my population table from some other table by that foreign key. That is not supported yet in Postgres. Update to this is maybe, I'm not sure if it's coming in PG12 or not. Unique constraints are enforced on per partition level versus global level. So if you have a unique constraint, that unique constraint is enforced on per partition level versus a global level. So that is also one kind of bummer. Major improvements of declarative-based partitioning is coming in Postgres 12. For example, there are some major performance improvements coming in, data integrity related issues are being fixed. So with all that being said, we said, okay, let's give declarative-based partitioning a try. So how did we implement a declarative-based partitioning? We created a partition table. Since I told that you cannot use a normal, you cannot turn a regular table into partition table. So we created a new partition table. We created child table and did partitioning by date of birth. If we did partitioning by date of birth, what that meant for us is we had to drop primary key support from our ID column, because primary key means unique constraint, and you cannot have unique constraint on a column other than the partition key, right? In our case, the partition key was DOB, right? So we had to drop the unique constraint and primary key support from the ID column. But row identifier for that column was still ID column. It was not hard enforced, but it was soft enforced by our application. Values in that ID column are still being auto-incremented using Postgres sequences. Postgres has something called as sequences, using which it auto-increments values. So we had dropped the primary key support from ID column, but ID column was still our unique identifier for those rows. What we did in our application is now all the new writes that are coming in are being done on the new partition table. The old data still exists in the old partition table. The second step we did was we copied all the data that is there in my old partition table in my new partition table using batches, and obviously it took hours and days to complete. We added relevant index to relevant column. So this is how we implemented declarative-based partitioning in our application. The noteworthy thing here is we had to drop the primary key support from ID column, and that led to downtime. And now you would say you implemented declarative partitioning, you said all good things about declarative-based partitioning, why does it lead to downtime? Because we dropped an index from the ID column. Now what was happening is, due to our ORM, right, all the updates were happening like update this data from this where ID is equals to this, right? Now ID is not an index column anymore, right? What that would doing is, that was still doing a full sequence scan, and since this was a write heavy table, the CPU shoots up to 100% and application went down. It took some time for us to figure out what is actually happening, but once we figured it out, what we just did, we did not add a unique index, we added a normal index on ID column. Now the update queries are using index like it was doing earlier, it's just that it's not unique anymore. What was the result? All big sequence scans got split into multiple small index scans, happening parallelly and by themselves. The execution plan that you would see here would say that, okay, execution time is still 1 second. You would say 1 second is very huge. It is huge, but think about it, this query was not even running in 100 seconds previously, now it is running in 1 second, and that is not a frequent part of our application, that is a part of application that is being queried once in a day types. Previously it was not queryable, now it is being queried just with, if you want to fetch the data of last 6 months, you can fetch in 1 second, and the number of rows returned by it is around 10 millions or so. So that was a huge performance boost for us. Some word of caution here, you might say, okay, declarative partitioning is good, I'll go home and implement declarative partitioning. But no, B-tree indexes is still great. I would say long-live indexes. You should look for alternatives only when you are fetching large number of tuples from DB. In those cases only, you should look for alternatives. Other than that, B-tree indexes, Brin indexes are great options. Indexes comes in various forms, partial indexes, composite indexes, full text indexes. So, and more often than not, combination of those indexes will work for your use case. In our particular example, we use RDS provided by AWS for managed database service to test out everything. So we did not have luxury to check PG Partman or PG Bench to unleash some advanced feature set of partitioning that Postgres does not provide, but those extensions provide. All the things that are presented in this talk are our personal experiences, observations, and might not fit for your scenario. So always test out everything, run, explain, analyze, and then see. Do not take anyone for their word, even the documentation, I would say. This is it from my side. I am open to feedback and questions. You can send feedback over Twitter also. You can ask questions directly here also.
How do you manage migrations with
Relations, like migrations, so migrations are automatically handled. I mean, by migration you mean adding a column, right? Good question. I'm not sure how does it do that, but if I am guessing it correctly, I mean, it should, in declarative partitioning, when you add a column, it should automatically route to appropriate table, but I do not know whether it's the right answer or not. I'm just guessing out. Because in our case, the table, we do not change that table. It was append only log kind of table. So in our case, we do not even think about this scenario. Anything else? Cool. I think this is it then.
Thank you. Thanks, Tarun.
Yeah.